All right, so it is a good time to see dedicated designs. We will start with MD5, which is very similar to, we will start with MD4, which is very similar to MD5, then SHA1 and SHA2, also RIPEMD. So let's start with MD4. This was developed by Ronald Rivest in 1990. Block size is 512 bits. Message digest length is 128 bits. That message digest length actually is here represented with ABCD. Okay, so all of them are 32-bit words. So this is a single round, but we have 48 rounds. So you repeat this process 48 times. So it looks like a face-style cipher, as you can see. This is a Merkle-Damgard construction. So just think about this picture 48 times. Okay, that function is actually RF in our Merkle-Damgard structure. Okay. So if you have two blocks, you have to perform 48 runs here, 48 runs here, and so on. Okay. So let's go back to our picture. So this is normally you put your IV here, not the message, but you start feeding your message 32 bits by 32 bits from here. Okay. So your message, your block size is 512 bits. But you feed 32 bits from here. Ki is a constant. Okay, this is just a rotation. And there's a f function here which just performs logical operations like XOR and etc. But this is also the same in MD5, so I will show it in detail in the following slide. So this is a very simple design from 1990, and generating a collision takes a few microseconds. So you can provide a lot of MD4 collisions on a laptop in a second, which maybe thousands of times. And there's an attack that finds preimage with 2 to the 95 operations. But as you can see, a generic attack would require 2 to the 128 operations. But you can find preimage in a faster way. This was IETF standard hash function defined in RFC 1320. Retired in 2011 with this RFC, so it is also something strange, it retired in this year, but it is, broken years ago. But this influenced later designs, MD5, SHA1, and RIPEMD. So let's look at MD5. This is again developed by Ronald Rivest 1 year later to replace MD4. So what has changed is as follows. Number of runs are increased to 64. And now there is also another addition here. Okay, so MD4, there wasn't this line here, but now you have it. And this square addition symbol actually represents addition modulo 2 to the 32. Actually, so you're performing addition on 32-bit values, but after 32 bits, you remove the carry bits. That is what I'm trying to say, actually. So you increase the number of rounds, you added one more operation, so it should be more secure. But still, you can find collisions. So in the previous picture, I haven't provided the details of FI. So FI is defined as like this. So let's go back. I said the number of rounds is 64. So in 16 rounds, you use F. In another 16 rounds, you use G, H, and I. So as you can see, for the 16 rounds, when you use F, it takes 3 inputs, B, C, D. But you perform AND, OR, NOT, AND operations. So these are just logical operations. Here in the G, you have something similar. Here you have XORs, etc. So a very simple design, a very fast design. The problem with MD5 is that collision resistance is not provided because generating a collision requires 2 to the 18 operations. This is very fast. You can do it less than a second on a very old laptop. Okay, so but I have to say that a lot of people in the world thinks that MD5 is secure. Okay, even I gave a seminar to teachers in computer science and realized that they teach as if MD5 is secure and they are using MD5 in their daily lives. But it was broken when I started working on cryptography, so I never used it. So it's strange that people are still using it. Okay. So preimage resistance also is not as good as the exhaustive search attack. So let me give some historical information. In 2004, it was shown how to create a pair of files that share the same MD5 checksum. In 2005, Lanstra, Wang, and Weiger demonstrated construction of two X509 certificates with different public keys and the same MD5 hash value. So it is a problem for digital signatures. In 2008, it is shown how to fake SSL certificate validity, so certificate authorities should stop using MD5. In 2012, the authors of Flame malware used an MD5 collision to forge a Windows code signing certificate. As you can see, a cryptographic algorithm broken years ago, but people kept using it, and at the end, you end up with a malware in Windows. So sometimes, you know, when you get a new Windows version, actually old broken cryptographic algorithms are replaced. Okay, but still, even in Windows 11, there are some instances where in the background MD5 or SHA1 is used. But of course, there most probably you don't need a collision resistance, but still, you shouldn't rely on that fact. So people should stop using MD5 and SHA1. And strangely, in Turkey, in court, people are still providing MD5 and SHA1 hash values, which shouldn't be, you know, any validity at all. Here's an example for MD5 collision. So this X1 is one input. It is 512 bits. X2 is different than X1. The same parts are shown as black, but the red parts show you differences. So here you have 7. In bit notation, this is 0, 1, 1, 1. But when you flip the first bit, you get F, which is 1, 1, 1, 1. Okay, so here actually we are performing a differential attack. We are making small changes, but both of these inputs provide you the same output. So this is what a collision is actually. Okay, you can generate many collisions like this in a second. Okay, so we move on to SHA1, developed by NSA. It was first published in 1993 as SHA0, but a small modification is made in 1995 and renamed as SHA1. Okay, so I think this rotation wasn't here in SHA0, if I'm not mistaken. Okay, because they realized that once you remove it, it becomes weak. But here the idea was to increase the message digest length. Okay, now it is 160 bits. So after D, now we have E, which is 32 bits. Okay. So idea is similar. You have the F function, you know, you feed the message from here, the constants from here, but now we also increase the number of runs to 8. So it should again be more secure. Of course, it is more secure than MD4 and MD5, but previous attacks, those differential attacks, somewhat become applicable to here, but require a lot of time and memory. So let me show you an example to understand how a hash function works. So probably this is from NIST documentation. So assume that I'm going to take the hash of the value ABC. Okay, so just create a TXT file, just write ABC inside it, then take the hash of that file, and you will obtain the following results. So I will show you the intermediate values, but of course you would only see the output value. So initial hash value, which is the IV, is put inside. This is here. Okay. So your message ABC are converted into hexadecimal. Okay. 61, 62, 63. Then you have the padding, 1 zeros. Okay. At the end, you write the length of your message in bits. So you have 24 bits here. So you write it here. Okay. So this is your message block, 512 bits. So this is what you feed from here. Okay. So initially IV is here. After one round, this is what you get. Okay. After the second round, this is what you get, and so on. So if you continue this way, at the end, this is the values for A, B, C, D, E. But you add the initial parts, to obtain the hash value. Okay. So recall that this was our IV. So let me go up. This is your initial hash value, IV. You add this to this output, and this is the finalization, and provide the hash value. So if you create a TXT file, write ABC there and take the SHA1 hash of it, the output should be this. If it is not, then your implementation is wrong. Okay. So instead of ABC, just flip one bit. For instance, just say ABD. The resulting hash value would be somewhat completely different. And I can show you an example in a minute. Okay. So there was an attack, theoretical attack by Wang years ago, and this required 2 to the 63 hash operations. But although this attack was old, even at that time, we could have obtained this much of computational power. But to find the collision, you have to also, store these hash values, but storing 2 to the 63 values is not practical. So in terms of time complexity, this attack is doable, but in terms of memory complexity, it was not. So what people did was to use the modern GPUs and perform a memory trade-off. So reduce the memory, but increase the time. So by time memory trade-off, these attacks become more practical. And currently we have collisions for SHA1. Okay. So for SHA0, the collision can be found with 2 to the 33, that's 6 operations. So you can understand why NSA modified SHA1 and obtained SHA2. Okay. Browsers of Microsoft, Google, and Mozilla stopped accepting SHA1 SSL certificates by 2017. Maybe you remember those years after 1st of January, after New Year's Eve. When you try to connect to a web page, your browser started to give, red errors. This was due to this fact. People updated their certificates from SHA1 to SHA2, and those browsers start accepting those web pages. So let's start with the free start collision. This was from 2015. So this IV and this message block for SHA1 provides this value. And if you change the IV and also the message, then it also provides you the same hash value. So we call it a free start collision because normally you don't have, you fix the IV and use it all the time. But here, if you look at this value, you have 91 here, 90 here. So this is not a problem in practice because in practice you keep using the same IV, right? So this was found by Mark Stevens and his team using only 64 GPUs, and all GPUs. These were good at the time, but now we have the 4000 series, and it required 2 to the 57 SHA1 evaluations. So a free start collision breaks the inner layer of SHA1, does not directly translate into a collision on the full SHA1 because the attacker is not able to choose the initial internal state. But here, Mark Stevens pointed out that he found a free start collision because the computational power he had was small. But this proves that if he had more GPUs, he could find a real collision. This is what he claimed. And Google said that, okay, we have a lot of GPUs, modify your attack, and let's find the SHA1 collision. And this is what they did. 2 years later, this is a real SHA1 collision. This is not a free start, so IVs are the same in this picture. And this is 2-block collision, by the way. So Mark Stevens' teams, together with Google team, found this collision. And there was actually a bounty on SHA1 collision in Bitcoin. And after this collision, the same day, somebody withdrew 2.4 Bitcoins of reward from that account by using this collision. Okay, so somebody became a little bit of rich after that. Okay, so SHA1 is broken, MD4 is broken, MD5 is broken. So what do we have? We have RIPEMD 160. Good thing is that this algorithm was designed by academicians, but not NSA. Okay, unlike SHA1. So The block size is 512 bits. Message digest length is somewhat changes, but this doesn't provide this amount of security anyway. So the most popular one is RIPEMD 160. It is again 60 rounds. Merkle-Damgard looks very similar to SHA1. But the good thing is that nobody found collision for this. And actually, Bitcoin uses this algorithm. And any Bitcoin accounts actually, actually your public key is just a point on an elliptic curve. So you take that value, first take SHA256, and then calculate RIPEMD 160 of it and give it to people as if it is your Bitcoin address, and people send money to it. So this is used in practice in many cryptocurrencies. So collision resistance due to birthday paradox to the 80, so nobody could find a collision. RIPEMD 160 is the only remaining 160 bits digest size hash function that has not been broken yet. It was developed in the open academic community in contrast to the NSA designed SHA1 and SHA2. So if you want short hash output, this is the thing that you want to use. Finally, we move on to SHA2, developed by NSA, first published in 2001. So it has different block size depending on the message digest length. Number of runs also, again, depends on which sizes you are using. It is, again, Merkle-Damgard construction. So until this part, we always seen Merkle-Damgard. So since the message digest length is increased, we have more words here. So this is why we have 8 words of 32 bits. Now we have more functions, like majority functions, sigma, and so on. And these functions are, I think, provided here, as you can see. So very similar to old designs, but now we have more words and so on. So currently there isn't any collision attack. So pseudo collision attacks break up to 46 rounds of SHA-256. Pyramid resistance. So I've seen a 2011 attack that breaks pyramid resistance for 57 out of 80 rounds of SHA-512 and 52 out of 64 rounds of SHA-256. So let's finish with SHA3. So since MD4, MD5, and SHA1 are broken, only SHA2 remained, but it was similar to previous designs, right? So people said that if this one also gets broken, what will we do? So NIST announced a hash competition. So this competition was held between 2007 and 2012. Received 64 submissions. 4 of them had Turkish designers. Unlike previous competitions, NIST allowed designers to tweak their algorithms after run 2. And if you want more info, you can find it in this web page called SHA3 Zoo. You can see all of the algorithms and what kind of attacks they received and so on. So, okay. So in the SHA3 competition, these are from that web page, SHA3 Zoo. These are the algorithm names, principal submitter, and this is the part where they actually eliminated. So these algorithms are eliminated in round 1. This actually shows what kind of attacks people found for these algorithms, okay? So a picture continues in this way. So in the round 2, these are the algorithms that got eliminated. At this point, there weren't much attacks for these algorithms, but security is not the only issue here. We also focus on performance and so on. And there were 5 finalists. 4 of them, of course, eliminated, and only 1 of them became the winner. And Ketchak was the 5th algorithm here, which won the competition. So Ketchak, winner of the SHA3 competition, as designed by Guido Bertoni, John Damon, Shah Peters, and Gilles Van Asse. So this time, as you can see, the message digest length is exactly the same as SHA2, because if you want to move from SHA2 to SHA3, it should be compatible. But this time, it is a sponge construction, okay? So in this case, the sponge function, as I already showed you before, the picture is like this. But this internal state, as you can see from here, is really huge, okay? So in AES, we show this block internal state, which is 128 bits by 4 by 4 matrix, bytes. But in this scenario, we have 3-dimensional representation. So this part is called slice. This one is called the column. This one is called the row, and this one is called the lane, and we represented with these colors. So if you look at the rows, Keccak chi function actually performs this operation, these logical operations. Keccak p function actually focuses on a slice and performs these operations. Keccak row function focuses on this part in the z coordinates. And finally, the theta function takes these two columns and, perform these following operations. So as you can see, I tried to show you pictures, but didn't provide any pseudocode or anything because I found implementing SHA3 really hard. And I generally use the reference code, but in the past, I tried to implement it. At some point on, I obtained a correct implementation, but I found it really hard to implement a function that's complicated like this. So if somebody is using SHA3, I'm assuming that they are using the reference implementation. Okay, but if you want to move on from SHA2 to SHA3, you can do it. The message digest lengths are the same, but contrary to all of the previous designs, as you can see, this is a sponge construction, not a Merkle-Damgard construction.